All right. Okay. Folks, let's graph the function f of x equals x cubed. When I plug in a 1, it spits out a 1. When I plug in a 2, it spits out an 8. When I plug in negative 1, it spits out negative 1. And when I plug in negative 2, it spits out negative 8. Folks, if you can't do that quickly, you got to do some work just plotting points. Okay? You do want to get comfortable just drawing these graphs fairly speedily. There's the graph of x cubed. Okay. And I just told you we didn't do the work, but we found that the derivative was 3x squared. What does that look like? Let's see here. When I plug in a 1, it spits out a 3. And when I plug in a 2, it spits out a 12. Okay. This is definitely an interesting graph. And it's got an interesting derivative. Notice that x cubed is always increasing, right? Is there anywhere where I have negative tangent lines? No, because it's always increasing. So the derivative is never negative here. Now there is one place where I have a horizontal tangent line. Where is it? It's right there. Do you see it? That corresponds, so that's at the, so the slope of this line right here is 0. That corresponds to that order pair 0, 0. Now careful, what is this 0 referring to? It's referring to the slope of the tangent line of the original function. Okay, so it's this 0 right here that informs us about the slope of the tangent line. 100. Oh, okay. Let's put another one up there. I'm going to put a tangent line right there. What is the slope of that line? Don't guess. We can find the exact answer just like that. Not 1. At 1. At x equals 1, what's the slope of that tangent line?
3.
It's 3. How do you get there? Well, you say, well, f prime of 1 is equal to 3 times 1 squared, which is equal to 3. We can also see that by looking at the graph of the derivative and seeing that it passes through the order pair of 1, 3. This 3 right here informs us about the slope of the tangent line of x cubed. Folks, this is the work you need to spend some time on. Okay? You've got to spend some time doing this work. It pays big dividends. All right, one more. What's the slope of the tangent line right here? By the way, what's this order pair? This is the order pair negative 2, negative 8, right? Okay, but I'm not asking what's its ordered pair. I'm asking what is the slope of this tangent line right here? What's the slope of that tangent line? 12. Why? Because f prime of negative 2 is equal to 3 times negative 2 squared, which is equal to 12. Sure enough, we see if we plug in a negative 2 into the derivative function on the graph, we've got the order pair negative 2, 12. Now, does the derivative ever tell me how the functional height, the y value of the function? Is there any way I can use the derivative to figure out anything about this point right here, this y value? The derivative doesn't tell me what my elevation is. Do you guys understand why I say that? You can think of your y values as your elevation. Your derivative doesn't tell you what your elevation is. It simply tells you whether you're going uphill or downhill. You could be on a mountain walking uphill. You could be down in a valley walking uphill. The derivative doesn't tell you what your elevation is. It just tells you how you are changing. This is essential. The derivative tells you how you are changing. It doesn't tell you what your current status is. All right. Okay. I want to talk about this. So folks, that n corresponds to you using that nth row of Pascal's triangle. Really what you're doing is something called the binomial theorem that I'm not going to get into, but that's how you prove this. Okay? But the coefficients of Pascal's triangle match the coefficients of the binomial theorem. So they're on par with one another. So that's where that n comes from. But way people like to remember this is they say, bring down the exponent and then subtract 1 from the exponent. And that's what we saw when we were generating that list, right? The list of derivatives we calculated. We brought down the exponent and subtracted 1 from the exponent. See this here? Brought down the exponent and subtracted 1 from it, because that's 2x to the first. We brought down the exponent, It's not really what calculus is, right? We're not really bringing down exponents. It's a result of having done this limit operation over and over again. Okay, so I'm going to skip the proof. Let's go ahead and apply the power rule. So, folks, now from here on out, if I teach you a shortcut in this class, you may use it. Okay? Now, on a test, you might see questions where I say, using the limit definition of the derivative, find this derivative. You cannot use shortcuts on those. Okay? So if I say use the limit definition, you can't use these generalized rules that we're developing. And you will have between 2 and 3 use the limit definition questions on your next exam. Okay? All right. So let's go ahead and practice using the power rule here. The derivative of this expression is 6x to the 5th. What happened? What was our function? It was x to the 6th power. What did the generalized power rule say? It said go ahead and put a coefficient in front of it that corresponds to the original exponent. Multiply it by x to the power 1 fewer than what you started with. Okay? So let's see here. This would be y prime is equal to 154x to the 153rd power. Again, unfortunately, in 10 years, this is probably what you'll remember about this class. Which is a bummer. Maybe make a note to yourself to try to remember more than that. Okay? All right. I'm going to go ahead and use Leibniz notation on this one. I'm going to write dy dt is equal to 4t to the 3rd. How we doing, folks? Okay. I kind of like using Leibniz notation on this one because the variable wasn't x. The derivative of y with respect to t. Everyone, let's read that together. The derivative of y with respect to t. Okay? If you're trying to avoid using Leibniz notation, that's a good reason to start using it. Okay? Because we're going to use both, and both notations have their merit in this class. Okay? All right, we don't know how to do letter D. Because we only learned the power rule for what to do if you've got a power function. This has a power function, r squared, but it's got a coefficient in front of it. Turns out that its derivative will be 3 times 2r to the 1st, or 6r. Can you see what's happening there? What did that 3 do? Just came along for the ride. Similar to your properties of limits. Okay, let's say that now. The properties of derivatives and the properties of limits are very similar. They have a lot of similarities. Constants come around for the ride. We will see that you can distribute derivatives over sums. Be careful, there are some distinct differences. You cannot distribute derivatives over products. Let's all say that together. You cannot distribute derivatives over products. Okay? I'm not going to talk about this one very much, but we've got then the generalized power rule that we'll prove in a later section. Okay? And the generalized power rule says regardless of whether n was a natural number or not, it could just be any real number other than 0, you take the derivative this way. Okay? I didn't put an example up here, so let me give you this one right here. If I gave you f of x is equal to x to the pi power, then what is df dx? It would be pi x to the pi minus 1. Everyone see what I did there? So it does not need to be a natural number. It just has to be something other than 0. Okay? Okay, let me put this example up here too, though, because people step in this all the time. Okay? If I give you g of x is equal to pi to the 3rd power, everyone write down its derivative. What's the variable? The independent variable in this function? X. How does this function change with respect to x? It doesn't, because it's a constant function with regards to x, right? So what's its derivative? Derivative of a constant function is 0. How many of you stepped in it? Don't be shy. Raise your hand if you stepped in it. Oh, I know there are more than that. Yeah, a lot of you stepped in it. It's easy to do, right? Be careful. Okay, make sure that you understand that the function has to vary with respect to the variable. All right. The next rule we want to talk about is the constant multiple rule. The constant multiple rule says that if you want to take the... So what do we know about f, first of all? Let's put a criteria on it. F is... Everybody read that word. F is? Differentiable. What does it mean to be differentiable? It means you can find the derivative. All right? What does f need to be? Differentiable. What? Oh, you guys are regressing. What does f need to be? Differentiable. What does that mean?
You can find the derivative.
You can find the derivative. Okay? You can't always do this procedure. Okay? Remember, we've seen instances where limits don't exist. All right. So, if you have a differentiable function, then the derivative of an arbitrary constant times that differentiable function is just the constant times that function's derivative. Okay? One way to say this is that constants factor out of derivatives. You can pull constants out of derivatives. Let's go back and look at our part D from up above. Does that make sense now? So rather than looking at the derivative of 3r to the second, I looked at the derivative of r to the second and then just multiplied it at the end by a factor of 3. Any questions on that? All right. Okay. So let's look at this. I want you to start thinking about this. So this is, actually I'm using the derivative as what's called an operator here. Don't worry about that word. Okay? But I'm applying the derivative to something. And look what I'm saying you can do. When you apply the derivative to a what? When you apply the derivative to a what?
To a sum.
To a sum, it distributes over that sum. Just like that should remind you of limits and a lot of other things we've studied in math class. Okay? Derivatives distribute over sums, or put another way, the derivative of a sum is the sum of the derivatives. Let me just add, you can take derivatives termwise.